Welcome to the Electronegativity and Molecular Polarity tutorial. This will be a closer look at covalent compounds. This is a very important topic. So let's get started, right? So when we talk about covalent compounds, we talk about electron sharing. However, if we think about it, what do we think that electrons are all going to be shared equally? No, right? But it depends on who is sharing. Okay, and I know I tend to personify the elements, and the more you get to know them, you probably will too. I mean, when I think about electron sharing, there's some people in my life I would share everything with, and there's other people I'm not going to be so generous with. And elements are like that too. So this idea of electronegativity, on a really simple level, we could think of it as electron greed. Some elements are very greedy, and they really don't want to share the electrons. It's like they become covalent compounds begrudgingly. If you look in your textbook, they will define electronegativity as the ability of an element to attract shared electrons to itself.
Just center the page a little bit.
Oh, this.
That was perfect.
Okay. Okay, so remember when we see shared electrons, right? So shared electrons, that's a covalent bond. All right. So here are the trends. So I have shown you the numerical values. Some students really like the numerical values, but you really don't have to know them that well. We can just go with the trend. If we look at the periodic table, right? And these trends tend to focus on the main group, the representative elements, the elements where we're filling the S and P subshells. And if we look at electronegativity, which is way too long to say, so we will abbreviate it EN, and we can see from these values that fluorine in this corner is the most electronegative. It's the greediest. And then if we look over here in this corner, in the cesium-francium area, we see that these are the least electronegative. And that makes sense with what we know about the elements, right? Because here's our stair-step line. And so we know to the left are the metals. And metals like to lose electrons. And then to the right of the stair step, we have the nonmetals. And nonmetals like to gain electrons. So these trends in electronegativity make perfect sense. Electronegativity increases as we move up the periodic table, and electronegativity increases as we move from left to right. So we don't need to memorize all of these electronegativity values. We simply need to know the trend. And then how these differences in electronegativity work is that at one extreme, we have the nonpolar compounds. And that's where we have equal sharing of electrons, so there's no distribution of charge. And then, as the difference in electronegativity gets larger and larger and larger, we've arbitrarily set a cutoff. That if the difference gets too large, we call them ionic compounds. And that's where we have a full positive charge and a full negative. So where things get interesting is in this gray region, right here, where we have the unequal sharing of electrons. And this creates poles of charge, where we have the partial positive. So this symbol here, this Greek lowercase delta, means we have a partial positive charge and we have a partial negative charge. And so this is where we want to focus our attention in this tutorial, where we have a difference in electronegativity that is in this middle range, greater than 0.4 if we use the numerical values, less than 1.8. Okay, so we've seen it on the table, but let's look, if we're looking at compounds, right? If we're looking at compounds, non-polar compounds means there's an equal sharing of electrons. So this is going to be elements where we have identical elements, like 2 hydrogen atoms. Or even fluorine. Even though fluorine's the most greediest of all of the elements, the most electronegative, if we have 2 fluorine atoms in a tug-of-war for those shared electrons, they're going to pull with equal force. So there are no poles created. And then a very important combination, even though carbon and hydrogen have a slight difference in electronegativity, we consider them non-polar as well. And even if we had like a double or a triple bond, notice that a polarity has nothing to do with the types of bonds present. Anytime we have a compound that's all carbons and hydrogens, it's going to be nonpolar. So nonpolar compounds are kind of boring. There's really not too much else to say there. It's the polar compounds that are of interest. So this is where we have an unequal sharing of electrons. And so we saw the symbols earlier. So we could describe it one of 2 ways. This is called a dipole moment arrow. All right. So the arrow points to where the electrons want to go. So that's where the partial negative shows up. And then there's a crosshatch on the shaft of the arrow to look like a plus sign. And this tells us where the electrons are missing. So we could use either one of these symbols. We could either use the dipole moment arrow, or we could use the partial positive and partial negative to indicate when we have a polar covalent bond. And so this is where we have, right, this is where we have a difference in electronegativity. So when we look at these examples, right, the first thing we want to do is practice our trend. So if we look here, if we have carbon and oxygen, maybe I'll just draw a periodic table right here. Okay, and then here's our buddy hydrogen. Okay, so if we have carbon and oxygen, right, based off of electronegativity, right, electronegativity increases to the right. So we would write our dipole moment arrow pointing towards oxygen because it's more electronegative. Or we could write a partial plus on the carbon and a partial minus on the oxygen. All right, so then chlorine's down here. So if we had carbon and chlorine, this one might feel a little tricky, but notice we're going 3 elements to the right and we're only going 1 element down. So chlorine is more electronegative than carbon. So once again, the dipole moment arrow is pointing to the right. But there's no rule how the dipole moment arrows will point. Oxygen, right? Hydrogen always loses. Hydrogen only has 1 proton, so it doesn't have a lot of power to attract the shared electrons. So the dipole moment arrow is going to point towards the oxygen, letting us know that because oxygen is more electronegative, the shared electrons spend more time with oxygen and less time with hydrogen, creating these poles of electrostatic charge. Now, one thing that can be a little bit confusing about these dipole moment arrows and these partial plus and minuses is we haven't put an actual numerical value. But all polar bonds, right, we saw on the page before that there can be a range of polarities. So let's look here at this type of question. Arrange the following bonds in the order of decreasing polarity. Now, this type of question, it's only reasonable to ask it if we keep one atom the same, right? So here's our buddy carbon. And then we're looking at how carbon is bonding to nitrogen, oxygen, and fluorine, right? So the greater the distance between two elements in the periodic table, the greater the difference in the electronegativity. So if we're going for decreasing polarity, we want to have the most polar, and the most polar means the largest, right, difference in electronegativity. The delta symbol means difference. Okay, and then we're going to decrease to the least polar. All right, so looking at these elements, carbon and fluorine are the farthest up. Oops, there we go. Carbon and fluorine are the farthest apart, so they're going to be the most polar. Then would come the carbon-oxygen bond, and then would come the carbon-nitrogen. So this would be the least polar. Alrighty, now these are important skills, recognizing polarity and understanding electronegativity. But this is a tool to help us understand molecules better. So now that we recognize the trends in electronegativity, let's apply them to entire molecules. So for molecular polarity, this is going to depend on two factors: the molecular shape and then the bond polarity. Okay, so molecular shape, this would be the three-dimensional shape, and there's a video tutorial available on molecular shape. And this uses the valence shell electron pair repulsion theory. So if you're feeling uncomfortable with me talking about molecular shape and Vesper theory, you'll want to go and review the video tutorial on this topic. And then for bond polarity, this will be the differences in electronegativity, which we've been talking about in the first couple pages. So we're going to take everything we've just learned about bonds and now apply it in three-dimensional space. So a nonpolar molecule is just like a nonpolar bond. There's no distribution of charge, or it's symmetrical and balanced. Versus a polar molecule, right? Asymmetrical means not symmetrical. Distribution of charge. So let's work our way through bigger and bigger molecules to see how this applies. Two atom molecules are very simple. It's the same as bond polarity. Right? So even if we have two, and I'll put the valence electrons in here, or the lone pairs, right? So even if we have two fluorines, which are the most electronegative, this is still nonpolar. And if we replace this with, for example, with hydrogen, now we can draw in our dipole moment with a dipole moment arrow, or with our partial plus and our partial minus. And so anytime we have a molecule with only one dipole moment arrow, we recognize this as a polar molecule. All right, so now let's get to some trickier ones. What happens if we have three atoms in a molecule? Well, let's look at carbon dioxide. Right? On the previous page, we noted that carbon and oxygen have differences in electronegativity, so we do have polar bonds here. However, this dipole moment is equal and opposite to this dipole moment, so they cancel out. So even though we have polar bonds present, we end up with a balanced, oops, let me slide this down, with a symmetrical balanced distribution of charge. So for CO2, it's non-polar. But we could have, let's look at ozone, right? When we do ozone, we now have a bent molecule. And so anytime, it's pretty simple. Anytime our central atom has a lone pair, we know it's going to be polar. But let's but instead of just memorizing something blindly, let's reason it out. Oh, well, plus, yeah. So even though these are all oxygens, the lone pair is going to pull, and that's going to create polarity. I think I'd like to do a couple more examples here. Another common example is sulfur dioxide. Oops, too many lone pairs. There we go. Okay, so when we have this bent arrangement, the oxygen pulls the electrons, and notice that now they're pulling, they're not canceling because they're at angles to each other. So it's also polar. Another trick that we can use when we're trying to determine molecular polarity is we can take the dipole moment arrows and put them, we call this the tip and the tail. For example, if we look at carbon dioxide, we have one arrow going to the right, and then the second arrow is going to the left, and we're back where we started, non-polar. If we compare that to sulfur dioxide, I'll do this one, we do this one in green, right? So I do the red arrow, and now from the tip of the red arrow I draw the green arrow. Now we see that we have a net dipole that we didn't get back to the beginning. So when anytime we have a net result, that's why it's considered polar. Alrighty, let's keep building up to some bigger molecules. If we have 4 atoms in a molecule, for example here, if we had this compound, if we're looking at the carbon, remember that the carbons and the hydrogens share equally, so we don't have to worry about drawing in any dipole moment arrows here. However, sulfur is more electronegative than carbon, so we will get a dipole there. This is a simple one. Anytime we draw only one dipole moment arrow, we know the molecule is polar. And that, oh, okay, and then another example would be, for example, we did like ammonia. So it helps to draw it in its three-dimensional shape. Right, so when we look at ammonia, remember that the wedge is poking out at us and the dash is going back. And then I'll direct you to the molecular geometry, molecular shape tutorial if this part's fuzzy for you. And now we know nitrogen is much more electronegative. So there's a dipole moment arrow, and I'm going to do each dipole moment arrow in a different color. But notice that they're all pointing up, and then we do get a bit of a pull from the lone pair. So because of the trigonal pyramidal shape and all of the dipole moment arrows pointing up, they're all pointing in the same direction. So that's going to be another example of a polar molecule. And then to convince you, let's try if we do, right, there's the red arrow. And then if we add the blue, and then the green, right, notice that we end up with a net dipole for ammonia. So it's a polar compound. It is possible for there to be nonpolar compounds. Let me show you one of those. If we had sulfur trioxide, remember that the double and single bonds do not affect the polarity. This is simply about the identity of the atoms. So here's the example where we would have 3 dipole moment arrows all pulling out, right? But they're all equal in size. So we have equal dipole moments, right? And then the geometry here is trigonal planar. So this is similar to carbon dioxide. It's like 3 spokes on a wheel pulling with equal intensity. So they all cancel out and the molecule is nonpolar. Alrighty, one last, we'll only go up to 5 atom molecules. So here, this would tend to be our tetrahedral arrangements. So this is where it can be very important to remember the 3-dimensional shape, because if we looked at this molecule here and we wrote out our dipole moments, we may very naively think that these 2 dipole moments are going to cancel. So it's important to see the 3D shape, right? It's tetrahedral. So when we draw this molecule, we need to draw it so that we are reminded of that 3-dimensional shape. Right? So the chlorines are not, right? This is not a square, flat molecule. The atoms around the carbon are radiating out into the corners of the tetrahedron. And so now when we draw our dipole moment arrows, we see that they're pulling in the same direction. Anytime our dipole moment arrows are pulling in the same direction, it creates a net dipole. And so this would be a polar molecule. Of course, if we take and we have all 4 atoms as chlorine, now we're back to the symmetrical charge distribution. Now this is just like carbon dioxide. We have 4 polar bonds, but these 4 polar bonds are all pulling to the corners of the tetrahedron. And so we end up with a nonpolar molecule. Alrighty, so now let's do a little bit of practice to see how you're doing here. So here are 4 practice molecules for you to make predictions about the polarity. So this first molecule here, right? All carbons and hydrogens. Anytime it's all carbons and hydrogens, nonpolar. Now we've replaced 2 of the hydrogens with chlorines. Here we notice, right, that both of the chlorines are pulling in the same, right? They're both pulling to the right. So that creates the net dipole. So this will be a polar molecule. Let's see what happens if we move these chlorine atoms around. Now the chlorine atoms are coming off of 2 separate carbon atoms. But once again, they're pulling in the same direction. So we're going to end up with a polar molecule. And then last but not least, now we have the chlorines on opposite sides of this double bond. Now notice it's the same size dipole, equal and opposite. So it cancels to create a nonpolar molecule. Alrighty, so I hope that you found this tutorial helpful and that you'll take the time to work some homework problems to reinforce your understanding.